Okay, thanks for inviting me. I'll talk about the performance evaluation using the Tau performance system today. And first I would like to thank my colleagues and collaborators who have helped with what I'm presenting today from OSU and University of Oregon. So the Tau performance system is a comprehensive profiling and tracing toolkit that provides a integrated, scalable instrumentation, measurement, and analysis components. Instrumentation as in inserting hooks into your program to perform the measurements for profiling or tracing, profiling with the wall clock time, with the hardware performance counters, and analysis tools such as paraprof that can show you the profile data that's collected in a run. Tau supports both profiling as well as tracing modes of measurement. The key differences in profiles, you see what's the total aggregate summary. What is the total time spent, the exclusive time spent in each routine, excluding the child calls. In tracing, you can see a detailed log of what happens when during the execution. So what each process is doing and every communication event. So Tau is an open source BSD style license toolkit. It uses performance and control variables with MVAPICH too, and I'll explain a lot more about that. One of its key strengths is that if you have a big code, a big application framework, Tau can be integrated very easily in the build process, and you can then compile your code with Tau and run and generate the performance data. You can download Tau from this URL over here. So what can Tau tell you? First of all, it can show you how much time is spent in key code regions at the routine level, at the statement level, at the loop level. It uses event-based sampling to show you the contributions at individual statement levels, or probes that fire off with start and stop calls to identify accurately what is the time spent at the loop and the routine level. It can also show you, besides wall clock time, it can show you how many instructions were executed in your code. You may be interested in knowing what was the extent of vectorization in my code. If you were running on a Knight's corner, Knight's landing kind of a system, using the VPUs can be critical to achieving good performance. You may want to know how many data cache misses took place in each code region that was computationally intensive. It can sort the data, it can show you exactly what was the instruction and floating point operation counts in key code regions. It can show you the memory usage of your code. You may want to find out what was the memory footprint. As the number of cores increase, you may find that your problem does not fit in on these new processors, that you may need to keep some cores idle just to be able to run a really large test case. In that case, you may want to know what is the maximum amount of memory that each of my ranks took, the memory footprint, and can I accommodate this on the new processor? So it can show you the high water marks, it can even show you when and where the memory gets allocated, deallocated. If there are any memory leaks, it can show you that. It can show you the I/O characteristics of the code, what is the peak read and write bandwidth, which files were touched, how much data did you transfer in each file, what is the contribution of each phase of your program, if you have representative phases that you can annotate the program in. It can show you the scalability features of your code, efficiency, runtime across different core counts by using a tool called Perf Explorer, which interfaces with the TauDB database. So you can upload the profile files to the database, connect the Perf Explorer tool, and then analyze the application scalability behavior. Now you can also answer questions like, how can I tune MPI for better performance? You can find out what performance variables that show the internal inner workings of the MPI are exported by MVAPICH. And then you can find out what are the knobs that you can turn, what are the control variables that you can use to tune the performance of MPI, and then you can set those and tau will propagate those to the runtime and talk to the runtime and exchange information. This is part of the NSF funded new project. So I do not need to tell you how great MVAPICH is and where you can download it, but I want to talk about how MVAPICH 2 interfaces with the tau performance toolkit. So here is the user, and you can see the applications that use tau and MVAPICH, they talk to each other through this interface called MPIT. So our goal is to create recommendations. Our goal is to show you what happened in a given run, and based on the engineering performance report, you will be able to see how changing one particular parameter affected the overall performance, or what was the difference in the total execution time of the program, what was the difference in MPI wait timings, and so on. Libraries like MVAPICH 2 are now reconfigurable at runtime. So you do not need to use a parameter, a tunable parameter from the beginning to the end of the code. You can change it at runtime, and that's our next step in the project, where we are going to evaluate how we can collect the performance data, evaluate it, do in situ analysis, and then modify the parameters at runtime and change the behavior. I have some examples later to show you, but this is overall the MPIT interface as proposed by the MPI 3 standard, and it's part of the standard, so different MPI implementations implement this interface, and MVAPICH 2 is the leading distribution in its support for the MPIT interface. So it exposes a rich set of performance variables and control variables. These PVARs or CVARs, as we call them, they get transmitted to tau, and we show that list in the metadata that tau collects. So you can launch a code, an uninstrumented code with tau, and then see the full list of performance variables that are there and what they mean, what they stand for, and the control variables, and specify the new values for those control variables. So you can tweak these knobs before running the program, and we'll add support for interactive performance engineering sessions in future versions. But we have just released tau version 2.25.2 today, and it supports the MVAPICH 2 MPIT interface in preparation for this talk. So you can download it from our website and check this. So you can have this report recommendation come out at different phases of your code, and then look at the overall execution of tau and do the control of your program. Here are some examples of how we include the control variables and what they can change. So in the first case, you can look at the maximum inline message size, where to which the inline transmission of data is supported by MVAPICH 2. You can look at the vbuff pool size, the MPIR CVAR for the vbuff pool size, which controls the internal communication buffers, or vbuffs as they are described in the MVAPICH 2 terminology, and change that pool size. You can also change the secondary pool size. If the pools that are allocated statically at program startup are all exhausted, then it allocates the secondary pools, and then you can change an MPIR CVAR eager threshold. Now we all know that there is a switch that happens between the protocols for communication. When you look at the asynchronous, non-blocking communication calls, and you see that for short messages it uses the eager protocol, and for long messages it uses a rendezvous protocol, where the metadata gets exchanged, then there is an ACK that comes from the receiver, and after receiver gives you the ACK, then the sender sends the message So you may find that it's important to know things like what is the average message size that my program is using. Okay? What is the threshold at which this change takes place from eager to rendezvous? Can I set my message size for the MPI runtime so that it's just a little bit higher than the average, and I might be able to get better performance in that case? So there are various knobs that you can turn, and now Tau is enhanced with support for setting these CVARs in non-interactive mode for the applications. Now, how do I run the program with Tau? So we have a new tool called Tau exec. It works transparently with your applications. It's very easy to launch your code with this, because if you are running your application in this way, where you say MPI run -n1024 and run your executable like this, all you need to do is say Tau exec with a set of options and then get it out. You do not need to change the code. You do not need to change the source code, the build, or the binary. It will LD preload an agent in the address space of the executing application. It will intercept the MPI calls from MVAPICH 2. It will interact with the runtime to set those variables, to query the performance variables, and then generate the profile data. So it's very easy to introduce it into your workflow if all you're interested in is the MPI information. There are other runtimes that it supports as well, including OpenMP, CUDA, and so on. And this is the example of the PVARs, the listing that you will see in Paraprof, Tau's profile browser, once you generate the profile report. And here you can see the list of all the PVARs and what they represent. Now, these values will be collected periodically by Tau by using an interrupt timer. And at the end of the execution, you will see the aggregated value for the entire run. And you can look at what it stands for. So, until now, we did not have support for reaching down into the MPI internals and then changing these using performance tools. But thanks to the work in the MPI forum and the MPIT interface, we have this bridge between tools and the runtime, which is used by Tau to then set these control variables. And then in Tau, you can see exactly what was the old value and the new value. Over here, there is the IBA eager threshold for the CVAR, and you can see what this is the switch point between eager and rendezvous protocols. So you can see the full listing of what options are available and then choose to set them. Now we have enhanced Tau so that we can set variables at runtime like Tau track MPIT PVARs. If you set this to 1, then you will see all the PVAR listing. If you set the CVAR metrics that you want to change, you can set these. Note that it can also take array notation, so you can have multiple for the same CVAR. If it's a vector, you can set various pool sizes in this case, and then give a comma separated list of values. Okay. So you got to make sure that the value that you specify doesn't have a comma in itself. Then set the path, and then just run Tau exec with the tags. The tags are the keywords that you use while configuring Tau, and I'll show you. But here's an example of using the vbuffs without the CVARs. Now, here the MPI application was run with the default parameters, right? So when MPI starts up, it sets the default list of variables and statically uses some number of vbuffs. And you can see the total memory used in the vbuffs over here, and you take these samples periodically, and then you might realize that the number available and the number used are such that you didn't need so many of those based on the vbuff listing. And so you might say, well, it looks like I over allocated. And so you could change that and set the size, like the CVAR vbuff pool size to 16, and then look at the performance again. And here you can see that the vbuff pools, the total memory used is reduced. So you can reduce the footprint if you don't need it. And here are some examples of what happens on every rank, and this is again shown in Paraproff's display. You can see the changes that happen with the CVAR and how it's represented. Here's a set of examples. You compile your code. Normally, you can say tau exec, and it will show you the MPI level data. You can say tau exec -EBS or event-based sampling. And then it will periodically interrupt your execution and also show you what happened at the statement level. Okay. You can also rewrite the binary and run it. And then finally, you can launch Paraproff and view it. There are some interesting tags that you can specify, and also which runtime to enable. So here we are using kubectl for GPUs, and you can use kubectl, OpenCL, OpenACC. You can use OpenMP Tools Interface, OMPT. It is in the process of being standardized. It's not there yet, but very soon it will be there. We have our own version of OMPT that you can download. And you can look at memory debugging, you can turn on event-based sampling like this, but with all of these, you must use some configuration tag. And what this tag is when you configure tau, you can specify the name of the compiler, you can specify where the MPI is located, include and lib directories and so on. You can specify location of external third-party packages like PAPI, which is used for profiling with hardware performance counters, or Beacon, which is a backplane for event and control notification. So you can do online monitoring of your application. You can use PDT for automatic source instrumentation. But each of these parameters, when you configure tau again and again, it creates a configuration file or a stub make file with some unique tags. You can also specify additional tags, and these are like PAPI, MPI, PDT, and you can set an environment variable called tau make file if you wish to recompile the program with tau instrumentation. If you wish to do that, there are compiler scripts which you can use. So instead of using MPI F90, you can just say tau F90.sh. It will just compile the code. It will create a binary that's instrumented at the routine level. It can also do instrumentation at the loop level. Then run it, and you will generate profile files. Here are examples of configurations of tau, and you can also use the -t parameter to target that configuration. So if you configure it in a certain way, it creates a make file and the libtau.so that finally gets preloaded with tau exec, and you can use these tags in tau exec to target a given configuration. PDT is what is used to instrument your source code. You can specify an instrumentation specification file to the instrumenter. It reads the source files, and then it generates an instrumented copy where you can compile the code. So here is the workflow without tau, and then you can just change the compiler names, export a tau make file, and then build your code. You can specify an optional instrumentation file which can include or exclude files or routines, or even instrument routines at the loop level. And this is how you install tau and use it. There are many compile time options, like say use compiler-based instrumentation instead of source. You can have many runtime options, like track the memory footprint of your code by just specifying this, and then you can see that Here, thread 0 took a lot more memory than the other threads. So there are some usage scenarios. For example, if my application is using a lot of memory and it's at say 98% of the total memory, and you want it to use less memory, at runtime you could tell MPI to reduce the number of vbuffs. You will save some memory, your code will not crash. It can reduce the memory footprint. Now if you are running your application and you find that a lot of time is being spent in MPI wait, what do? Maybe the problem is that it's using the rendezvous protocol when it should be using the eager protocol. So how do you find that out? You can say tau com matrix equals 1 and look at the total message size, the average message size, and you could say, okay, my code's running most of its messages at 30,000 bytes, but the eager threshold is just 16,000. So what if I shift that eager threshold to 31,000? Then I'll use eager protocol for the rest of my processing, and you'll be able to see a difference in the MPI wait time. You can also use tau for online monitoring of what's happening inside MPI as the code is running by using the beacon API and the GUI. There are many other runtime variables. I will not go into them. I mentioned com matrix over here. There are others that you can look for memory debugging. Here are examples of the 3D display for tracking the communication. You can look at the extent of vectorization in your code by sorting the data based on wall clock time and see that out of 8, you are reaching like 7.3 or 3.4 in key regions. You can visualize the overall topology of your code with the 3D topology browser. Here's a 3D view of the code in paraprof. You can see each thread of execution. You can see all the MPI ranks and how much time was spent. In short, you can see the shape of your profile with paraprof. That can give you a good idea about what's happening in your code. You can also see a timeline view using JumpShot or Vampire. Vampire is a commercial trace visualizer that you can get a demo license from Paratools. And you can see what happens at each point in time. We have a new option called -score p equals download in tau, which will automatically download what is necessary to build OTF files with tau. And you can also use an OVA file where all of these tools are pre-installed and you can just launch it in a virtual box. You can see this for some more information. There are some more pamphlets and a tutorial guide available over here. If some of you are interested in learning more about tau, they are just kept outside. And again, feel free to drop us a line and let us know. This is Eugene, where we are located, University of Oregon. We have a very active visitor program. If you would like to come and spend a couple of days in Eugene, please talk to me and we can arrange for that so that you can optimize your codes. I would like to thank our sponsors, the National Science Foundation, for their support of our project, the Department of Energy and Department of Defense, the PET program from the Mod Office, and our partners and NASA, and our partners from the Ohio State University, Paratools Inc., University of Tennessee, Knoxville, from PAPI, TU Dresden, the developers of Vampire, and ULS Supercomputing Center, where ScoreP is developed. Any questions?
So let's thank Samir.